Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Kostas Alexis, who is a full professor at the Department of Engineering Cybernetics at the Norwegian University of Science and Technology. So something about Kostas: he obtained his PhD back in Greece in unmanned systems control and collaboration. Then he was for a while a senior researcher here at ETH, actually, in Roland Sigvar's group. And then before going to Norway, he was an associate professor at the University of Nevada, Reno. In general, in his research, he wants to contribute towards establishing true navigational and operational autonomy for robotics, and especially aerial systems. Some highlights of his research, as you can see in the bio, is that he was leading the team CERBERUS, who is the team that won the DARPA Subterranean challenge recently. Among others, there were also some ETH people there. And also another fun thing that I read about and I found interesting is that he contributed to a world record in setting the endurance for autonomous flying vehicles below 50 kilograms. And they were able to make it fly for 81.5 hours. Today,
with Roland's group.
With Roland's group, yeah. Today, Kostas is talking about resilient autonomy in perceptually degraded environments. And I'm personally excited to hear more, and that's why I give you the stage, Kostas.
Thanks a lot. Thanks for the invitation, and thank you everyone for joining. So indeed, I'm going to talk about resilient autonomy in perceptually degraded environments. So let me preamble my talk with a small video that shows a bit of mixture. It's kind of an old video at the moment in terms of results, but still I will say paints the picture I want to start and motivate this talk. So the whole idea is that I believe, of course, this is to be debated, but I believe we have reached a good point where robots in relatively benign environments can work fairly reliably, right? And of course, I think this is not really a very wild claim. We see this with industry being developing and so on and so forth. But it's very difficult to have systems that operate in perceptually degraded environments. And by perceptually degraded, I might mean, for example, whatever renders the optimization problem of a sensor for localization, for example, or anything like this, degraded or degenerate, like a self-similar tunnel for LiDAR, a lack of visual texture for vision, obscurance such as smoke for vision or LiDAR, and so on and so forth. And this is in stark contrast with, for example, we operate with vision and we don't seem to have problem with in most of these environments, or at least be able to have some ability to mitigate the effects of degradation in such environments. So I want to discuss how we can build systems that are resilient against conditions of perceptual degradation, whatever is the nature of these conditions of degradation. So let me just now go to my next slide and not show all the video. And I believe that if we achieve autonomy across conditions of perceptual degradation, then we are one step closer into this vision of autonomy anywhere. And the images here just show examples of what is anywhere in my mind, in most of which we have tested, with the exception of space, and we have not reached these depths of underwater, really. But in the majority, in an underground cave, an underground mine, in an industrial facility subject to smoke, in a ballast tank from a vessel, a nuclear power plant, and so on and so forth, a snowy forest, etc. There's a lot of conditions that robots are supposed to operate for a collection of tasks, be it inspection, being exploration, being data gathering, being manipulation eventually, and then you have also other systems in the overall loop, and so on and so forth. So I have this definition, which is not coming from robotics itself, about what is resilience. I have repurposed a definition about economic resilience into the domain of robotics. And the claim is that to have a system that presents resilience overall, then in systems and methods on board the machine, you need that you have, of course, redundancy. You cannot just depend on a single component. Robust performance, but how do you fundamentally achieve robust performance? The main second claim I want to mention is that you must have resourcefulness. And what I mean by that is that if, for example, you depend on a single methodology to do your localization, and you depend on localization for all subsequent tasks, then it's prone to fail eventually once this particular system is exposed to the condition that makes it degenerate. But if you have interleaved multiple ways that you could do localization in a multimodal fashion, number one, and if you have different ways in your navigation stack that you could survive for short or long term, or anyway for sufficient amount of time or space, even in the breaking event of localization, then you have a system that presents resilience one way or the other. And I'm going to be talking today across these loops, but fundamentally, I'm going to be talking mostly about perception, and I'm going to be talking about control also that takes into account also high-dimensional data, like images, depth images, and so on and so forth. and allows for navigation even when localization is drifting, for example. And by control, I here mean a deep learned policy, but of course, this extends also to combinations of neural nets with MPC and so on and so forth. And we have some work about this now, the combination, but this is not going to be in the slides. So let me start with the more straightforward aspect of it. Let's consider that we have an environment that is GPS denied, as relatively typically we have in many cases, dark, so therefore with limited texture. At the end of the day, obscurance like smoke or dust, so we have limitations on how far away we can see with LiDAR, and with vision, self-similar, narrow, large scale, and so on and so forth. And the idea here is that all conditions that I just mentioned do not happen simultaneously, right? So we might be GPS denied and self-similar, for example, but we are not self-similar and with no visual, for example, no visual feature and no material to see, for example, with the use of a radar or something like this, right? So there is the idea that these degradation conditions happen, but they don't happen all together. So, back in 2018, when we started the DARPA Subterranean challenge that was mentioned, we worked on a cascade solution of bringing this together. And at this point, the decision for a cascade solution was motivated by a simple fact. If we start with a cascade solution, this means we can take components we have built or the community has built and put them together in a function that allows us. So we focus on the optimization problem, for example, for LiDAR, so where it breaks, identify the conditions which ended up being reflected in the eigenvalues of the underlying Hessian, and we found a way to cascade solutions in order to have a method that, for example, as is seen in this video, although it's a self-similar tunnel, because we have the combination of vision, LiDAR, and IMU, when LiDAR is failing in the self-similar tunnel because the point clouds become identical as you proceed in this long tunnel, then the combination of vision, IMU plus LiDAR naturally makes it work. And I just want to start saying, although I'm very happy that we won the challenge, this is a solution that allows you to get that far. It's not necessarily the solution that is more generalizable or more flexible across all environments and all cases. And it's also at the same time not the most beautiful solution. So I think we are looking for a solution that should allow us to combine sensors without having to define heuristic functions that need thresholds that one way or the other might be environment specific or sensor specific to a less extent. So during the challenge, for example, but also later, we have departed into a work that eventually wants to replace the first keyword that you see. It wants to be tightly coupled multimodal SLAM, but I'm going to start from one example of loosely coupled multimodal SLAM, and then I will get to the more tightly coupled solution. So in the more loosely coupled multimodal SLAM, you can build a nonlinear factograph that either over the whole horizon of the map or in a sliding window through IFL optimization, you can attach constraints coming from the optimization of the solutions of different problems. So you can have, for example, visual inertial constraints that are represented as odometry updates, represented here as transformation updates, so constraints that represent this odometry, LiDAR constraints, and so on and so forth. And it's still loosely coupled because you have the different constraints not representing the features that the modality is tracking. So, for example, let's say corners and surface patches from LiDAR, and let's say, orb features from vision, but represents the odometry update as a transformation, which means, in fact, there are different solutions running in parallel and co-optimized result-wise in a common factograph. So it's still loosely coupled in that sense, right? There are different solutions, which means that we have to define also heuristic functions. When we solve this problem all together, and we write the collective optimization of this problem, either in ISAM2, so the full map, or in IFL form, so the sliding window representation, we solve this problem, but I'll just give a motivation. If, for example, LiDAR has failed in one axis, like in the self-similar tunnel, so the x-axis is at this point broken, we are still attaching a wrong information, and we are then bound to either give it a huge covariance, let's say, or something like this, huge variance along this axis, in order to make sure that the solution of the combined factograph is not attached too much on this solution, but rather, let's say, on the vision update, which in this scenario should work. And in the case of LiDAR, again, we do this, for example, by thresholding the eigenvalues of the problem you see here. And for example, if we have a general odometry solution that we have an associated covariance coming, and this odometry can be from anything, can be from vision, can be from anything else, then we can track the growth of the covariance, and we can play with some basic theory of optimal experiment design, and we can use a metric that represents some sort of entropy or a optimality or D optimality, and threshold at some point the growth of the error in this particular odometry update. Now, this still gets you enough ahead. And for example, this is the solution this is actually in Switzerland, with animal walking in a tunnel. And we are going down a self-similar path. And eventually, on the left, the old solution breaks at this point. And on the right, we have good continuation of the correct map without breaking, right? And on the right, we also have here, I'm not going to show this, we just remove the data from LiDAR and we have a more organic attachment to the vision solution. But now, to go further, we want to see two particular aspects. First, how we select the modalities that truly allow us to go through conditions of difficult degradation, such as smoke or dust, so obscurance. And the second, how we make the solution to be more tightly coupled. On the first front, earlier work of ours had focused on how we deliver thermal inertial odometry, because in many types of obscurance, but not in all, thermal, like long wave IR, is not affected. So a case for them, for example, would be dust or theatrical smoke of that nature, right? And you can formulate, again, a sliding window optimization problem with marginalization of both the pose that you have and the features that you are tracking over a window. And you can solve this optimization over the sliding window with all poses within the window and the landmarks that we are tracking from thermal vision being co-optimized within the window. So we have the current view and also selected keyframes over this window. And this method is direct, which means that essentially we're not extracting features, but we're extracting key points. And on the key points, on a large number of key points, we are directly optimizing an error that in traditional terms will be what we will call photometric. Here it's radiometric because it's thermal vision. And the motivation behind using a direct formulation is because in thermal data, it's much harder to have clear corners, clear features, as we typically have in well-lit visible spectrum images. And this is the formulation that you see here. And for purposes of computational efficiency, we solve this problem from a higher level of the pyramid, low resolution to the full resolution of them. And this was again back in 2019 or so, where we had this test and we had a LiDAR map of the environment, and we demonstrate that we get comparable results as with LiDAR odometry should you be having a map just with thermal inertial fusion alone. And that's what's an independent test to motivate the fusion, for example, of thermal vision into the overall complementary SLAM pipeline, modality complementarity SLAM pipeline. And this was already still work that was done for the DARPA challenge and so on and so forth. And you see the result that you see here, right? And if I was to let the video play, and I will do so for a while, you will see that other methods in visual inertial methods repurposed for thermal fusion fail. And they don't fail because they're bad methods. On the contrary, some of them are among the best methods, at least back in the day, and they remain among the best today to a large extent. The two reasons why these methods tend to fail is the reasons are the following. The first, that they are not exploiting the full resolution of the thermal image, which is a mostly engineering change. Simply, you don't have significant gradients. And therefore, because you don't have significant gradients, it's best to use essentially the full resolution of the 16-bit image. That's mostly an engineering change. After you apply this change to these methods, they also mostly tend to fail if they rely on traditional small features, so small patches of images, which are very difficult to match with accuracy across thermal images that are very vague, as you see here. And you see some of these results of these other methods now very quickly failing in these environments as the video plays. But I want to move more into this idea of departing from loosely coupled solutions and bringing ourselves closer to a tightly coupled solution. So I will talk. I'm not going to have a video here because this is actually being prepared with my students at the moment. But I think I will just motivate the method a bit more, have the presentation, and have the final result about it. So in this case, we have a drone that is operating, for example, in a fog-filled hallway, and it's pretty dense, as you can see here. Now, the moment LiDAR, for example, is that dense, and this is a Rev7 offset in particular, then whatever return you are getting from the LiDAR ends up being this very degenerate point cloud that you see on the bottom. So you know how to read Arvis plots. This is 1 meter box, essentially the grid of Arvis. So although it's in a long corridor, it's roughly 50 meters plus. You don't see more than 4 meters away than you, 4 or 5 meters or something like this, right? So it's a physical limitation of the device and of the processing of the returns from the device. But it's standard to expect that you might have this quality of LiDAR data, for example, this environment. So say you want to do a search and rescue in a smoke-filled environment, that's something that can happen. And you also see the inset view, which is a radar point cloud. And the point cloud, of course, looks not appealing to a certain extent. But here we think, should we, for example, do a loosely coupled approach, develop a radar inertial odometry pipeline, and then fuse it with LiDAR, which potentially could be an avenue. But what we are more interested to see is what if we bring constraints in a factor graph coming from velocity updates, so exploiting that every point in the radar point cloud has also Doppler velocity attached from radar. And second, attach on the factor graph all features from LiDAR. So, for example, let's say LOM-like features, so essentially corners, surface patches, and so on and so forth, co-optimize and eliminate the need for us to find out different odometry solutions, for example, from LiDAR, identify which degree of freedom is degenerate with a heuristic, and then try to inflate the covariance accordingly. But rather solve for all the constraints together, and therefore let the optimization find the correct solution in a more organic way. So this is what the factor graph will look like. So there are many constraints that there are two visualized for features, plane factors and line factors for LiDAR, but in principle, there are approximately together 600 of them co-optimized on every single pose. Radar LiDAR IMU is synchronized. We have the IMU factor, of course, super-integrated, and we have the radar factor that exploits velocity information, as mentioned. The radar factor comes as shown like a prior for every factor attached. And there are these four factors in the IFL optimization, the sliding window optimization, and represent what I just described earlier. So LiDAR terms come from the two types of factors we are using, line and plane features. Inertial terms come from plane integration over the stacked amount of IMU readings. It was on 200 hertz through this particular data set, for example, and radar terms exploit the fact that we have Doppler velocity and it's a varying vector, essentially, the particular point, and we formulate an odometry update for it, and we attach it as a prior into the factor graph. So that's more or less a drone that we built that integrates these sensors. It's kind of the same drone in many of relevant experiments. And this is a result that you will be getting should you, and I have to update a little bit the figure there because Saturn form is from another figure attached. But that's what you're getting, right? So you're getting, with a cyan plot, the correct map as the robot is navigating within this building, and the corridor that's at the bottom is the one that's filled with smoke. And if you just run LiDAR alone, it fails. It's our solution, so it's and it's expected, however, that all LiDAR solutions or most LiDAR solutions, I don't want to make a full claim. I would say it's very likely that most LiDAR solutions will fail in an environment that the point cloud is so degenerate. And if you run radar inertial odometry, you get a solution that works odometry-wise, but it's drifting. And again, this is our solutions. And the scale of the environment you see with a 10-meter block there. So I want to take a pause here and highlight this the direction we want to take. And we want to fuse in the same tightly coupled fashion all modalities and keep this computationally efficient. And now the previous result that you saw was run such that all the computation within the sliding window optimization is done within the 100 milliseconds, actually the less than 100 milliseconds, from the moment we receive the last input from the radar, LiDAR, and IMU sensors up to the next 100 milliseconds that we have before the next 10 hertz update comes, right? So we want to make sure that everything, of course, runs in real time, which becomes an increasingly more tricky task the moment you add modalities in this tightly coupled fashion, because you are solving a large optimization problem. And to that, we go into, and we have implemented this work into questions, how you select the best features, how you essentially reduce the information that you are inserting into the optimization without otherwise, of course, affecting negatively your localization and mapping result. So now I'm going to take a pause and ask this question of, yes, but indeed, in your experience, as in our experience of most of us, I would say it's pretty common to say that one of the reasons why autonomous robots are prone to fail in an environment is because localization drifted. And from, I started my research from a control standpoint. And at this point, discussing with my professor, and no bad claim about my professor, but it was just his view about the problem, is that, well, we should assume that estimation is working up to some extent with a modelable uncertainty. And the model was kind of standard, like some box constraint or something like this. And then we can work on the control problem. But in the continuation of my research career, I found that it's more likely than not that localization or some other problem of estimation is the failing point of our autonomous systems. So in the last years, we have been looking to the question, can we develop a navigation policy that exploits a low-level controller around states that we know that they can be reliably estimated, for example, the attitude of a multi-rotor system, so roll pitch yaw, actually roll pitch and yaw rate to be accurate, and then exploit in the deep learned navigation policy high-dimensional inputs, for example, depth data, visual data, LiDAR data, and so on and so forth, and develop the navigation policy that allows us to keep going in the direction that we were going when localization was working and mapping was working, even in the absence of localization and in the absence of a dense map from LiDAR or from vision or anything. And the assumption that we have, and we have seen this in practice, is that we can have an odometer that is drifting, but drifting slowly, that if we were to trust it, we were very likely, for example, to crash in the environment. But we can develop methods that for an amount of time, some seconds, some minutes, can get us to where we are going, even in the absence of this data. So we are looking for a navigation policy that does not rely on maps, does not require position feedback, does not require online mapping, and is allowed, it's possible to just exploit the high-dimensional input of the sensors, exteroceptive sensors, alongside a partial state, for example, with attitude, let's say acceleration, and maximum velocity estimate that are typically drifting more slowly, and get the robot in the desired direction. So this is a method we call Oracle, and we are about to open source it on Monday. And Oracle is represented in these two levels, up and lower. Oracle itself uses the following inputs, uses a depth image, and uses also a partial state estimate, which involves roll pitch, yaw rate of the system, and then the linear velocities. And we also have the covariance attached to those. And because we have the covariance, we can get sigma points, right? For this covariance, we can sample the covariance through the sigma points. And we give these inputs to a neural net alongside a heading vector of the direction it's supposed to go based on the information we had up to the point that SLAM was working. And we also feed this neural net with a stack of potential motion primitives. And this might be with motion primitives that are just based on integration of the trajectories of the robot, based on some other algorithm. There's variations in our work. And then we train a neural net such that at each level of a cascade set of neural networks through essentially an ensemble, we identify which of these motion primitives is most likely to be collision-free and get us the direction we want to go. So this means that essentially that's the more close-up view of this part of the methodology of the methodology of Oracle. You use the depth image, has the uncertain partial state with both the mean but also the sigma points, and has the stack of motion primitives. The processing part essentially is motivated coming from ResNet, and then we have later a bunch of fully connected layers that allow us to estimate the collision probability, or a score essentially that acts like collision probability over the path being in collision. And because this is essentially a classification task, you see the BC term prevailing in the beginning. Now, up to this point, I will say it's a pretty straightforward task to achieve, and you train the system, but it's very difficult for it to have robust sim-to-real performance. To have robust sim-to-real performance, we observe two facts. The first that we have, the first is aleatoric uncertainty, and aleatoric uncertainty in this framework relates to the unmodeled uncertainty in simulation. So, for example, the uncertainty over the partial state that I described before. So, and for doing so, we are getting the uncertainty transfer, and we are sampling multiple sigma points, and we will be evaluating the collision scores for all possible sigma points, not only the mean estimate of the platform. The second is epistemic uncertainty of the neural net, for which we are going to develop, essentially, going to take the information we have, the motion primitives I described, and we're going to put them in a deep ensemble of neural nets. So the uncertainty transfer accounts for the aleatoric uncertainty over the covariance of the partial state, and the deep ensemble will account for the epistemic uncertainty of the neural net for a collection of tasks that we cannot really perfectly model in simulation. For example, incomplete depth data that appear due to errors of stereo matching in practice, reflective objects that lead also to gaps into our stereo data. Very thin branches, for example, are very difficult to be captured, let's say, in the depth image, and you will see some results about this also later. So we took this work and maybe just one more time, eventually the deep ensemble and the uncertainty transfer are just added into a mean average fashion, weighted mean average, but then it arrives to a collective collision score. So we took the results and we do a test that this robot is not using position update and is not using a reconstructed map. It's only using the partial state that I mentioned that goes up to velocity. And alongside that, it uses the, this didn't want to run properly. Let's see if this time, yeah. It uses also the depth map that I mentioned, the online depth map, and flies the robot in the absence again of a working SLAM solution towards the direction of the heading vector that I mentioned that comes from the last point we had workable SLAM. And this is a short mission, but essentially now we have tested this system also in forests and so on and so forth. Now I want to go beyond just navigating in a safe manner, because the moment that we developed this method, it appeared to us that it's relatively easy to add extrinsic motivations into the system, such that when it's flying to a destination, it can also do implicit information gathering that can support future tasks, either because by observing more of the environment, it will allow a SLAM solution to recover, or because we are looking for something interesting in the environment. So we had done some work back in 2016 that we wanted robots that not only explore geometrically, but also look towards silent areas, essentially by replicating work from computer vision about visual attention and silence. And what we could do in this framework is that we could go back to Oracle, augmented with a parallel set of operations to another neural net that use the depth image and a detection mask over parts of the image, or pixels of the image, that represent areas of interest. Now, this could be the key points that come from some visual tracking algorithms, could be areas of interest like an object detector or something of that nature. And you also get a score of which of the motion primitives, if to be followed, will give us maximum information. And you can train this in a privileged manner in simulation, where you can have a full exhaustive planner that looks towards, identifies all trajectories, takes a lot of trajectories, and sees which one gave more information by using access to a map and being able to do reprojections of the point that's trying to look towards the camera and the localization of the system. So we train this with privileged information, with a map and with position, and we deploy this in an environment where the robot, again, is missing position information or access to a map. So a very simple test case is this that I'm gonna show here. The robot is starting, and there are these red backpacks that it has a reason to look at, right? It's just mostly a lab scenario. And the robot is flying towards the desired direction, but also taking small deviation of its path to look towards the points of interest. And it's important to highlight also that in this result that you see, indeed, the odometry that we were running did fail, and but it failed slowly. The losses were still okay, and therefore, to see the Oracle method surviving and performing in a safe and robust way. All right. Now, a good criticism of these methods that we also had is that it's trained end-to-end on synthetic data, which puts a high barrier onto the quality of synthetic data and how close the synthetic data are in practice compared to real life. And into that, in the attempt to reduce this into real gap, we thought to repurpose or redesign our neural net by first decoupling, modularizing a step that uses the depth image to arrive to a latent space that's of low dimensionality. This latent space will be subsequently trained through the same fully connected layers of Oracle. But this latent space should be trained in a manner that allows us to use also real data. So this latent space is in fact trained now through a VA. We have recently, it's to appear in December. We also have a new method that is not really a variation of the encoder, but what we call a deep collision encoder, and allows us to only focus on the information necessary in the image to predict collision for a robot of a certain size, because then this simplifies the problem and allows us to reduce the latent space even further. But let's consider now this case of this semantically enhanced VA. So it's a variation of the encoder for which we are also taking specific pixels that we consider hard to reconstruct in a very low dimensional, high compression latent space. And this typically, for example, might be thin objects or reflective objects and so on and so forth, for which we have limited information in the image, small amount of pixels. And therefore, with aggressive compression, they are prone to be lost. We increase the loss terms in the training of this variation of the encoder to focus on the semantics that we want to retain in the image. And we achieve roughly 1,000 times compression in our recent deep collision encoding work, which is already on archive. We achieve 4,800 times compression with allowing ourselves to do collision avoidance. And these are examples in these images, right? So this image here, all the small pixels that you see coming out from the branch of the tree are very hard to be reconstructed on the depth image. They're very hard to be perceived with a typical sensor. They're very hard to be retained on an aggressively compressed latent space. So we make sure that in the loss function, these are amplified. And we train this with privileged information, number one, on synthetic data. And we also train with real data. And real data will have some of these limitations because some of these things will not be perceived. But the combination of synthetic data and real data typically allows to go far away. And we have tested this also in areas with very thin branches. So these are, again, further examples. You see the results of the semantically enhanced VA reconstruction versus a vanilla VA that, of course, loses some of the thin features. And this is the overall view of this algorithm. So again, we have the VA train. We extract the latent space. Then it's the fully connected layers, much analogous to Oracle, where there's an RNN component, which allows to predict better the action that we should apply to the robot to move to the desired destination. And these are results that we see with these methods, which are roughly on par with the previous methods, with the exception that we can negotiate thinner obstacles more safely, number one. And number two, we can train with real data the main part that compresses the depth images, which is something that essentially pays out the more data we have in our stack. But I think this is also very applicable to companies, because companies that have access, of course, to data eventually can have many more benefits by having a method that allows them to assimilate real data as part of the control policy they will be deploying. Right? So that's an example. And last thing I want to mention, we have an extension of the same principles into using RL. We are using essentially this deep collision encoder that I mentioned. The deep collision encoder gets the depth image, makes essentially an effort to inflate along the distance of the depth image, so 5 meters, 10 meters, and so forth, exactly with the size of the robot of interest. And therefore, we have an inflated image, which is, however, inflated correctly along the range of captured by the depth sensor. According to the size of the robot, this image therefore represents typically less information to be encoded, which allows us, by training accordingly, to arrive to a very aggressively small latent space. This is only 64 variables from 640 by 480 depth image, which is 400,800 compression. And then we train with asynchronous PDO and RL agent to achieve pretty much analogous tasks that I mentioned before. Again, I don't have the video for this because we are compiling this video these days, but the result is similar, and you kind of see the path as mentioned before. And the reconstructed collision image is what you see here for this depth image, for example, right? And this is the key, I think, for more robust sim-to-real transfer for the systems, while also retaining that everything runs, of course, computationally very efficient. The overall RL component is roughly 3 milliseconds in this work, and then the other part, which is the collision encoding, is roughly 45 milliseconds, which allows high update rates collectively on the system, which then allows us to exploit faster dynamics. And the last thing I want to say methodologically, before I just make a small detour to say some things about our experience in DARPA Challenge, it's about autonomous inspection path planning. And I only mention this because the results in the challenge also run this essential component, although not being necessarily the main part of my talk. But of course, we care for methods that allow us to explore and map the world efficiently. And in particular, this old work now, but we keep updating, and we have most updates also in our open source repo, allows walking or flying or ground systems anyway to explore environments efficiently by working in a bifurcated fashion, first locally in a box, let's say 50 by 50 by 50 or 100 by 100 by 100, but a small box anyway. Does a relatively exhaustive search with a random graph. I'll say this is, again, mostly about getting some good established ideas and then bringing them to fruition in a manner that is efficient. And then in this global graph also exploits environment presentations that are very informative. Like, for example, we care for traversability. We embed traversability constraints, slopes, negative slopes for the object, make some prediction about how a shape of a voxel maps leads to a negative slope, and so on and so forth. And then this essentially was what allowed us to operate safely with walking or flying robots in the DARPA Subterranean Challenge. And we alongside, of course, the main work on locomotion also from our colleagues from ETAs that guided animals control, essentially the more like true navigation control. And then on the global level, it stores frontiers, stores intersections, areas that are maybe worth revisiting, and allows to negotiate kilometer-sized environments in an efficient way. And we had several components, either to just detect a frontier or to detect an intersection in a mine, and so on and so forth. And we attach all these areas worth to be visited later when the robot exhausts a certain area of exploration. So you can see some results here. This on the main video, it's a 37-minute long mission with animal. Back in the day, that's 2021 now. That's 1 month before actually the finals of the DARPA challenge. And the robot will just go into many places, find dead ends, will then recover from this global graph, continue the exploration from another point, and so on and so forth. On the right top, you see this method bifurcating between different modes now, not only exploration, but also doing inspection coverage. So first online makes a map, builds the map with LiDAR, then makes sure that everything is observed with vision, and so on and so forth to deliver results for the maritime industry. This is inside the ballast tank. And on the bottom right, you see actually the first video from this method back in 2018. And now I just want to, I'm not going to talk about all settings and all environments we test, but I'm just going to focus a little bit on the DARPA challenge for those that may not be familiar. So there we wanted to explore areas that are subterranean and diverse subterranean environments. So being, for example, an underground mine, underground cave, an underground, let's say, industrial facility. They had organized this in what was called the tunnel circuit, which was mostly underground mine, let's say, the urban circuit, which was mostly an underground urban facility, like a metro station or a power plant, and so on and so forth. And then the cave tunnel, which was natural caves. And DARPA did eventually some amazing job to get a huge environment, was called the Kentucky mega caverns. And inside there, they used part of the natural environment of the mega caverns, and they also built parts of it that looked what was an underground mine and looked what was an urban underground environment. And in the cave segment, also, they built a narrow part, and then they also used the large mega caverns of Kentucky. And the whole idea of the DARPA challenge was that robots are deployed from outside. No one is following inside. There is only one person that's allowed to contact the robots and communicate throughout the mission when communications are there. And you were getting a point if you were detecting an object of interest and localizing within 5 meters of error within ground truth, of course, calculated from DARPA. All that had to happen, of course, real time or online. And the mission was 60 minutes long. And the winning team was the one that detected more points, so more objects, and localized them correctly within the 60 minutes stop. So CERBERUS, which comes from, I'm Greek myself, so comes from this mythological creature of protecting the underworld, had the idea that we develop a team of walking and flying robots, this animation back in the day that we're preparing the proposal. And I led the team starting from Nevada, and then I moved to my group at NTNU in Norway, and it was my good colleagues, Roland Zigvard and Marco Hutter from ETH, was Mark Muller from Berkeley, was Maurice Fallon, who joined us maybe 6 months down the road, so pretty much from the beginning, from Oxford, Flyability, Sierra Nevada Corporation, and that was essentially our consortium leading into the project. And I think you get the idea what this is about, and you get our robots that we developed throughout. The rover is the only thing that didn't really had a significant scoring function by design, although we used it for scoring in the first tunnel circuit, so in the first competition event, and allowed us to actually pass to the second level. And the other systems were more like those that we used essentially in the later years of the project. And these instances that you see are from the environments, the left and the right, so the left and the middle are from the final environment of the DARPA challenge, and on the right is from the urban circuit, which is a power plant, nuclear power plant in Satsop in Washington state. And just mention things that I find interesting as lessons learned. The first lesson that we all learned through this process is the importance of field testing our activities, not for the sake of going and making a test, right, but for the sake of repetitive tests to the point of finding the problems in the algorithm, both finding fundamental problems and, of course, finding the system integration problems that are, always occurs for competitions. And this is the testing regime on the left. So a lot of tests in the US, a lot of tests in Switzerland, some tests in Norway in the last, phase that I moved, some tests in the UK, and so on and so forth. And this is, I'm not going to play this video, it's 60 minutes. It's super accelerated, so it's kind of incomprehensible really here. But here you will see essentially instances of the exploration with a team of robots from our side. And we detect in total 23 points. And this is a bit more understandable actually. So we detected 23 points, 23 objects, and localized them correctly. For all points we detected, we actually report correct localization. So that's also a testament for the quality of the SLAM solution. We had very little essentially effort on the human side, so on the single operator of our team, Marco Transato, who was at this point at RSL and currently is on a spin-off. And you see the points coming, and you see the localization, which was just the detection of the object was just below the localization was based on retrojecting rays on the reconstructed map from the SLAM solution. And eventually that's how the collective map looks like from all the robots. And this is where all the points of interest, all the objects that we detected are detected. And gray is the true ground truth from DARPA. And we had the opportunity, as mentioned, to win the competition, but actually I want to state the quality of our competitors. CSIRO, first of all, they had exactly the same score with us, but unfortunately for them, the tiebreaker was who reported the last point earlier, and we were the ones who reported the last point earlier, but otherwise they had also an excellent run. Marble from Colorado, Boulder, Denver, and Scientific Systems plus UCSC. Explorer, which was Carnegie Mellon, Oregon State. Costar, which was primarily JPL, MIT, KAIST, LTU, but also others. CTU Crash, which was CTU and ULaval Laval, Canada, and then 2 companies, right? And we got a nice prize reward and a nice congressional recognition from the US Senate, just for memory. And the last thing I want to say is that we do open source a lot of things that we do. So a lot of the work also from DARPA Challenge is open source, and you get some of the links. And among the highlights, I will say, is actually those 3. So the whole process for autonomous exploration planning from the DARPA Challenge, an ESAC gym simulator for flying robots that allows you to run very efficient. So it's up to 10 to the power of 6 when no depth sensors are there, and roughly it's 50,000 robots trained simultaneously on a 2 GPU machine when depth sensors are there. And Oracle, which is the navigation policy dimension, both the one with attention and not attention, and the one that exploits the variation autoencoder, which is going to be actually open source on Monday, Tuesday. So if you are interested, just send us an email if we haven't answered by this point. With that, I want to mention that we are hiring on many fronts. So we have 3 new projects starting. One started and 2 more hiring. One is, but I'm going to pitch only this one because we are trying to find very good people for this. It's about co-evolving the RL navigation policy of drones and their airframe and their body. So for those that have interest in these domains, please contact us if you have interest to join our group. And with that, I want to thank you for attending and glad to take any question.
Thank you very much, Kostas, for the great talk. Also, a lot of very cool videos. Let's open the stage for questions. You can either raise your hand and ask or write in the chat and I can read the question for you. Who wants to start? Okay. There is a first question in the chat from Julio Betancourt. Thank you for your talk. It was really inspiring and interesting. As the drone is navigating, I'm curious to know if there is a distinction between static and dynamic obstacles. And if you already tested the control architectures while considering dynamic obstacles, what would be the expected behavior?
The answer to that is that yes, in practice, no in method. So I think that the importance is the method. So our methods currently, up to the point that's published, take the assumption that the environment is static. Now we do have the things that everybody has, some big has outlier rejection, so it works when things are slow and so on and so forth. The last line of work that I mentioned for navigation policy using only the immediate depth images and the RNN will deal with slow dynamics in the environment. But the honest to God methodological answer is no, we don't deal with this in a principal fashion. But it's something we are actively looking to at the moment.
Right. If this answers your question or not, just follow up. Any other question? I have maybe one. So the short version is what's up now, but I elaborate on that, which is so now you won the competition. You also show what are the challenges ahead, but what would be the next competition to win here? In the sense, is the same competition but doing better on the performance metrics you were already evaluated for? No. Or are there new things that you think should be evaluated?
No. So, I mean, I'm not going to say only my personal interest into what is next, because there are many things that are next and everybody's doing their own research about this. But what interests me in the future is the following. So I think there are some fundamental limitations. There are 2 fronts. Improving, as you say, what we already do, which is not what I'm going to focus in this answer, and identifying core limitations that we have, and maybe it's worth looking ahead. So I come from 2 perspectives into this. My first goal is how we make sure we have systems that don't fail. And second, how we have systems that have significantly better performance than what we achieve today. I'm going to start from the last. My first main observation that I use to guide my next steps is that for many robots, we have become a bit too of generalists for good reasons, right? We try to use the same platforms all the time, and then we try to improve methods on top. But just because I started my research with interest in flight, I must say that flying quadrotors is the most naive thing we do in terms of having good performance across certain missions that are, for example, indoors or in complex environments. So I'm very interested into co-designing navigation policies now with optimizing or redesigning from scratch, not minor optimization, but redesigning from scratch the airframe of a flying system. And this is what we're trying to achieve in the project we call SPEAR at the moment. And not to be bounded just by replacing positions of propellers and changing the configuration of propellers, right? We have to see from actuation to sensing to navigation policy in a closed feedback loop of design. So that's the first thing. I think we need much better performance fundamentally, and do so, and this is the main thing I want to say, do so in an environment and mission specific way. Because of course, if we care for a solution that is equally good all around, we were likely to go back into a system that is designed much like the systems we design now. But the first thing I read when I was starting my PhD was that the quadrotor, which was given a quadrotor from my professor at this point, start with this, was that this is a design that has its roots in the beginning of the 20th century, and we are 100 plus years ahead of this. So the first question is, can we actually stick to engineering principles, not trying to do biomimicry or something like this? At least that's my approach, and have a design loop that takes into consideration how the system can perform given a specific navigation policy, and design together navigation policy and system and airframe. And on the safety, I think there's a great value on research, for example, on control barrier functions and so on and so forth, that has been worked by the community. But there is also great value into bringing this subject to the uncertainties and complex sensing principles and so on and so forth of robotic systems. In other words, to certify navigation policies, reflecting, however, the complex uncertainties and high dimensional inputs that we have on autonomous robotic systems. So these are two main fronts of research for me in the future, alongside, of course, we have some projects that are about improving what we already do, as you say. So we could do DARPA Subterranean slightly better, but of course, if we do DARPA Subterranean slightly better, then it wouldn't be a DARPA problem anymore, right? And beyond the DARPA terms, I think the competition is good to push some research in an accelerated manner, but we also need these more open-ended questions, like the one I tried to elaborate in the beginning, for which we're going to have slow results, but hopefully results that can have more impact down the road.
Thank you. This is interesting, and it resonates a lot, especially the first point. And connected, I think, to the first point, there is Anton asking a question. Thank you for the amazing talk. Have you considered working towards making the aerial system more resilient, not just in sensing, but also in design and control? For instance, instead of always detecting objects and avoiding them, being robust to collisions? And if yes, how do you think
we have published work on this? Yeah, we have published work on this, but I would say our published work on this follows the engineering idea that you have a system that essentially it's a rigid piece, and we design some metrics about kinetic energy that is to be during impact and so on and so forth, and we design planners that can explore being collision aware up to a certain point that is acceptable. But exactly to the point of the question, we're currently investigating two avenues in parallel. One that is a bit more complete at the moment, also still ongoing, and one that's to start. The one we're investigating with more completeness is compliant airframes that we model the compliance, and by modeling the compliance, we also exploit it in planning and in control. And by compliant, I don't mean at the end, right? I don't mean the end effector. I mean actually compliant, for example, between the arms of the system and so on and so forth. But the more interesting point is the point that I mentioned before, right? Which is, can we let automated algorithms, for example, evolutionary algorithms, design our system subject to principles, of course, because things have to fly, and there are specific principles we know that have to hold for a system to fly and to fly in an effective manner. But can we let them be designed purely driven by how well their navigation policy works? Because currently we design systems for them to be good in terms of air qualities, as we will call them in manned aviation, and then we design a controller around it, and then we design SLAM, and then we design path planning, right? Maybe with trajectory optimization and so on and so forth. But I say the more interesting question is, what if we let this be co-optimized? There is some excellent work from from Phi about optimizing some humanoid-like in simulation, which is very interesting, and I think this is a little bit inspiring. And this is more or less the direction we want to see in the future, or want to investigate in the future.
Thank you. Any other question for Kostas? if not, I think you left your email. It was, I think, in the first slide or in the last slide for these people want to reach out for.
It's in the lab link for sure. So if you just go there, you have all the information.
Also for the openings you have. Very nice. Thank you, Kostas. It was great having your talk here and great seeing all what you're doing, and good luck also for the next steps.
Thanks for the invitation. Likewise for you. All the best, and we'll be in touch.
We'll be in touch. Take care. Have a good night.
Bye-bye.
Bye-bye.